Well, hello everybody and welcome back. We are going to start talking about Chapter 10 today, which is the Independent Samples T-Test. Our last T-Test, which is exciting. So we'll be talking about how to conduct an Independent Samples T-Test. Just to review where we are, we've so far covered 3 hypothesis tests, and today will be our 4th. We started with a z-test, a one-sample z-test, where we had one sample. We had a population, and in that population we knew mu, the mean of the population, and we knew sigma, the standard deviation of the population. You needed to know both of those things in order to do a z-test. And what we would do in that case is take a sample from the population, treat the sample, and basically compare the sample mean to the population mean. And if the sample mean was different enough from the population mean, we would say that the treatment had an effect. And if the sample mean was not very different from the population mean, we would say that the treatment probably did not have an effect, and that any difference between the population mean and the sample mean was likely just due to sampling error. Then we went to Chapter 9 and we did a single sample t-test. This is very similar to a single sample z-test where you have a population, but in this case you either know mu, the population mean, or you estimate mu, and you don't have to know sigma, the standard deviation of the population. We estimate sigma based on the standard deviation of the sample. So a single sample t-test is in essence an estimated single sample z-test. And when you do that, the structure of the test is fairly much the same in that you have a population with a known or estimated mean. You take out one sample and treat that sample, and then you compare the sample mean to the population mean. And again, if the sample mean is very different from your population mean, you would say that we reject the null hypothesis, that we think that our treatment had an effect. And if the sample mean is not very different from the population mean, then we would say that we are going to fail to reject or retain our null hypothesis, and that we think any difference between the sample mean and the population mean is just sampling error. We then went on to Chapter 9, the end of Chapter 9, paired samples t-test. At this point, you don't need to know anything about the population. This is much more used in terms of a test that we do when we conduct research, because we very often don't know the parameters of the population. We often don't know the population mean or don't know the population standard deviation. And so a paired samples t-test allows us to conduct a test with 2 samples. Those 2 samples have the same participants, so you're basically doing kind of a before and after study or a pre-test, post-test study, where you test a group of participants, then you give them some kind of a treatment, and then you test them after the treatment. And if you recall, we calculated the different scores, right, between the pre-test and the post-test, and then did all of our statistics on those different scores. Now we're on to an independent samples t-test. This is probably the most commonly used type of t-test, in that we have 2 samples. Again, you don't need to know anything about the population parameters, but now these 2 samples have different participants. This is probably the kind of test you think about when you think about research, where you're comparing 2 different groups of individuals, like let's compare men and women on a test of verbal ability and see who shows higher levels of verbal ability. Or let's compare 2 different patient populations. Let's compare children who are diagnosed with attention deficit disorder and children who are diagnosed with autism on their memory ability, where you have 2 different groups of individuals, and then you're comparing the 2. Okay, So an independent measures design or an independent t-test allows us to evaluate mean differences using two separate samples, and that's the key. So an independent measures design has two separate or independent samples that nobody who's in one sample would also be in the other sample. This is different than our between subjects or paired t-test, where everybody in one sample is the same as everybody in the other. So an independent measures design can be used to look at differences between two totally different populations. Like I said, let's compare men versus women on verbal ability or math ability or statistics ability, whatever it is, or two different treatment conditions like a medication group and a no medication or placebo group, something like that. The people in one sample are different than the people in the other. That's the key. That's how you know it's an independent samples t-test, that there are different people in each sample. So this is used when we have no knowledge about the population, so we don't know population means, we don't know population standard deviations. And as with most of our hypothesis testing, the general purpose is to determine whether the difference between the two sample means is a real difference that you think would hold up in the population, or do you think the difference we get between our two sample means is just the result of sampling error? So let's start this and see how it works. Here's an example. In this case, we have two groups of individuals. We have children whose parents are married and children whose parents are going through divorce. So two groups of individuals, we've got 10 people in each group, and we're measuring their physical health score, or PHS. And our research question is, are children, or does the marital status of a child's parents affect their physical health? And so this first individual whose parents are married got a 77 in their physical health score. Maybe this is some kind of questionnaire they fill out. And this next person got an 88, the next person a 77. And then remember that this group is all different people. These are children whose parents are going through divorce, and these are their scores. So with an independent samples t-test, you're interested in the difference between the means of your two samples. How different is the mean physical health score of children whose parents are married compared to the mean physical health score of children whose parents are going through divorce? How extreme is the difference? And if you take a look here, this could represent the distribution of the two different populations we're interested in. Let's see, this green one is a little bit lower. So let's say this is the distribution of children whose parents are going through divorce. And here's their mean physical health score. And of course, there's variability. Not every child whose parents are going through divorce has the same physical health score, right? There's variability, but here's the mean. And let's say this blue distribution represents the population of children whose parents are married. And these are their physical health scores. Again, here's the mean physical health score that's higher than the mean physical health score here of children whose parents are going through divorce. And there's some variability in this distribution as well. And so the question becomes, how extreme is the difference between these means? You could imagine if I could, push these distributions together so that they line up on top of each other. So here's the green distribution, and imagine the blue distribution is right on top of it, and the two means are exactly the same. Well, in that case, we would say, nope, there's no difference in physical health score between children whose parents are married and children whose parents are going through divorce. And then as you kind of stretch apart these distributions, you become more and more likely to find that the parents' marital status does have an effect on children's physical health scores. And if you could imagine that these distributions are really far apart, like the green distribution is all the way over here, and the blue distribution is all the way over here. So you see a very big difference between the means. In that case, you're probably going to find that there is a significant difference of your independent variable, in this case, marital status. All right. Before we can do anything, we have to compute the mean and sums of squares for each sample. And so we first compute sums of squares for the two samples, and I'll show you how we do this. And then the hypothesis test really follows the same procedure that we've done in Chapter 7 and 9. So if you don't have a calculator, please grab one. We're going to do a bunch of calculations, and this will really be helpful for you if you follow along and try to do the calculations before you see the answers, okay? So here we go. Here are the parents who are married, and we've got 10 participants here, and the 10 participants whose parents are going through divorce. So first I want you to find the mean and degrees of freedom for the first sample. This is the married parents who are married, and then the mean and degrees of freedom for the second sample. So add up all the scores and divide by the number of scores, which would be 10 in this case, and then add up these scores and divide by 10 to get your mean here. And degrees of freedom, if you remember, is the formula of n minus 1, our favorite formula. So for parents married, it's going to be add up the 10 minus 1, so there's 9, and same here for parents going through divorce. So go ahead and find the mean, degrees of freedom, and once you've done that, you can pause it and then go on after you found the mean. And here we go. We've got 10 people in group 1. The mean was 79, and degrees of freedom here is 9. For parents going through divorce, again, we have 10 people in our sample. The mean here is 68, so the mean physical health score for children whose parents are going through divorce is 68. And degrees of freedom, again, is 9, which is 10 participants minus 1. All right. At this point, what we need to do is find our deviation scores and our square deviation scores. And we just have to do this for both samples. Now that we have two samples, we've got to kind of do everything twice. So, for instance, in this case, the score is a 77 for this individual. We're going to minus the mean, which is 79, which gives you a deviation of -2. And then remember, we square the deviation, so that's going to be 4. 88 minus 79 will give you the deviation score, and then square it. We're going to do that for this whole group of parents married. And then we're going to do it for parents going through divorce, but this time we're using, oh my goodness, I'm sorry, the mean of 68. So 87 minus this mean of 68 gives you your deviation, and then square it. 77 minus the mean of 68 gives you your deviation score, and then square it. So if you would go through and do all of these for me, pause it here till you're finished, and then once you are, move on. And hopefully you have this as your data. Remember, the deviation scores work just the same as before, where if you add these up, you will get a 0. And if you add these deviations up, you should also get 0. And so that's a good check to be sure you're doing this correctly. And here are your squared deviations. Next, we've got to find the sums of squares, which is just adding up the squared deviations here for parents married to get the sums of squares for this. And add up the squared deviations on this side for parents going through divorce to get the sums of squares for children whose parents are going through divorce. All right. I'm not sure why I don't have the answers here for you, but we will do that in 1 second, and then we're going to go through all the steps of the t-test as we've done before. So, population IV/DV statistical test. So our population, now we're looking at two populations because we're comparing two different groups. We're interested in all children whose parents are married, that's our first population, and all children whose parents are going through divorce. The independent variable here is your parents' marital status, and we're looking at two levels. The levels are married and going through divorce. And our dependent variable, what we're measuring, is the physical health score. Statistical test is an independent samples t-test because we've got two separate groups and we do not have the same people in each of our samples. Hypotheses. State our hypotheses. We, as always, have a null and a research hypothesis. The null hypothesis says there's no difference between the means of our two groups. Remember, the null hypothesis is that the independent variable has no effect, and so we end up with a hypothesis that looks like this. mu1 is equal to mu2. So mu1, this will be the married parents, so the mean physical health score of children whose parents are married will be equal to the mean physical health score of children whose parents are getting divorced. In this case, we're saying there's no effect of the independent variable, that the two means should be equal to each other. You could also write it like this. mu1 minus mu2 is 0. Again, if these two means are the same, and if you subtract them, then you'll get 0. I tend to like this first one better. It seems to make more sense to me, but either one is correct. Then we've got the alternative hypothesis, which is that the independent variable does have an effect. So in this case, we have mu1 does not equal mu2. The mean physical health score of children whose parents are married will not be the same as the mean physical health score of children whose parents are getting divorced. And again, you could write it mu1 minus mu2 is not equal to 0. That's another perfectly acceptable way to write the hypothesis. Okay, now we've got to compute standard error. And we've got some formulas. They look scary. When I teach this class in person, this is usually when I get a few gasps from students. So if you did the same thing, like, oh no, don't worry, you're not alone. But really, these formulas are not difficult. They just look a little scary, and we'll go through them and make sense of them. Just to show you where they come from, for instance, in our one sample t-test, to find variance, we took sums of squares and divided by n minus 1. Remember, because we have a sample, so we do n minus 1. And now we know n minus 1 is the same as degrees of freedom. So it's really sums of squares divided by degrees of freedom. And now for our pooled variance, this is the sample, this is the symbol for pooled variance. We now take sums of squares for group 1 plus sums of squares for group 2. So it's the same as this, but now we've got two groups, over degrees of freedom for group 1 plus degrees of freedom for group 2. So it's really just taking this formula and expanding it for two groups. And then to find standard error, here's our standard error for estimated standard error for a two sample. It's the square root of your pooled variance, which is what you just found here, over the number of people in group 1, plus again your pooled variance over the number of people in group 2. And even though in this example we've got the same number of people in both groups, that isn't always the case. For an independent samples t-test, you can have a different number of participants in each sample. It doesn't matter. You could have 10 people in group 1 and 20 people in group 2. Whereas with a paired samples t-test, remember, you will always have the same number of people in both groups because you've got everybody in the first group has to be the same as everybody in the second group. Okay, so here are the two big formulas, and it's also a matter of the order of operations in order to get these numbers correct, so I want to walk you through them. So in this case, all right, we needed sums of squares for group 1 and sums of squares for group 2, which I didn't have that answer for you. But if we added up the sums of squares for parents married, you should get 850, and so that was all the way back here. If you add up these squared deviations for parents married, you should get 850. And if you add up the square deviations here, you should get 1002. So those are your sums of squares for both groups. I'm sorry, I didn't have that. So in this case, for the pooled variance, you take sums of squares 1 plus sums of squares 2, which is 850 plus 1002. You add those up first, and then you divide by degrees of freedom 1 plus degrees of freedom 2. In this case was 9 plus 9. And in this formula, you add up the top, you add up the numerator, then you add up the denominator, and then you divide. Okay, that's the key for the order of operations here. So we add up the numerator, 850 plus 1002 gives us 1852, divided by 9 plus 9, which is 18, which gives you your pooled variance of 102.89. Once you do that, you now take this pooled variance and plug it into this formula. Now this formula is a little bit different. We've got the square root of, this is 102.89, our pooled variance, over 10, which is how many people were in group 1. And then you do that division, plus, again, pooled variance, 102.89, divided by 10. You do that division. So in each case, it's 102.89 divided by 10, which if you move this decimal point over, right, 1 point, it's 10.289 basically here, plus 10.289 here, which gives us the square root of 20.57, and then you do the square root of that, gets you to 4.54. So please practice on your calculator so that you're sure you're getting both of these answers and you're figuring out how you do the formulas. So in this case, again, it's you add up the numerator, you add up the denominator, and then you do your division. And in this case, you do this division, you do this division, then you add them together, and then you take the square root. Okay, so after all that, we have our estimated standard error of 4.54. To determine the critical value, we need to use our t-table again. I'll tell you that let's say we're going to use an alpha level of 0.05. And degrees of freedom in this case, there's two different ways you can figure out degrees of freedom for an independent samples t-test. You can either take the degrees of freedom for group 1 plus degrees of freedom for group 2. Which in this case was 9 plus 9, which is 18. Or you can take your total number of participants in both your groups, so we had 20 participants in total, minus 2, which also gives you 18. So there are two ways to get degrees of freedom. You either do degrees of freedom for group 1 plus degrees of freedom for group 2, or total number of participants minus 2. In this case, either way, you're going to get degrees of freedom of 18. So here I've got degrees of freedom of 18, proportion in 2 tails, and I'm looking at the 0.05 level. And if I bring myself around here, it looks like I'm at 2.101. Is that what I got? Yes, plus or minus 2.101. Okay. And this is just like before, where we've got a population. We have our critical value, 2.101, negative 2.101. And now we need to, next step, calculate our test statistic. Our formula for a test statistic for an independent samples t is sample mean 1 minus sample mean 2 minus mu1 minus mu2, and we're testing this, we're always testing the null hypothesis. And what did we say? Mu1 and mu2 under the null will always be the same. right? mu1 should be equal to mu2 under the null hypothesis. So this always turns out to be 0. So you really can almost ignore this part of the equation, over our estimated standard error, which we just computed. So in this case, we've got 79 for the mean of group 1, so that's the mean physical health score for parents who are married, minus 68, which is the mean physical health score for children whose parents are going through divorce, minus 0, as I said, this is always 0, so you can almost just ignore that, divided by our estimated standard error, which we just came up was 4.54, which gives us a t of 2.42. Once you do that, come over here, and we've got 2.42, which is somewhere over here. And by now, what hopefully you're starting to realize, that if we've got a t-value that is past the critical value, we're going to reject the null hypothesis. It's in that critical area, we're going to reject the null. Our obtained t, so our statistical conclusion, we reject the null. Our obtained t of 2.42 is more extreme than the value of the critical t, which is plus or minus 2.101. In words, so our substantiative conclusion, based on our data, the null hypothesis is rejected. There's a statistically significant difference between the physical health score in the group of children whose parents are married compared to those whose parents are getting divorced. In other words, the children whose parents are married have significantly higher physical health scores than children whose parents are getting divorced. And that's important. We need to know that they're higher. Which group is higher than the other? If you just say significantly different, it doesn't really tell us anything. How do you know they're higher? Well, you could go back to the means. We know that the mean for the parents getting divorced, or parents married, was 79, and the mean's physical health score of children whose parents were getting divorced was 68, so we know that's higher. You could also go back to your chart here, and you see that you've got a very high score, so we're saying that the married parents' score is higher than the children whose parents are getting divorced. Okay, so now we've gone through it once. You know me by this point. We're going to try it one more time. Again, keep your calculator out. I'm really hoping that you will follow along, or make sure that you're able to do these calculations, just pausing as we go through this PowerPoint. So students were randomly assigned to take an in-person driving lesson or a virtual reality driving lesson. So 21st century, right? At the end of the class, all students took the same driving test. Is there a difference in the number of errors made on the driving test for students who took the in-person versus the virtual reality driving lesson? Okay, so here's our data. Here's the students who took the in-person driving test, and here are their scores. And remember, these scores are number of errors that they made. And here's the students who took the virtual reality driving lesson, and here are the number of errors they made. And you can see here that we've got a different number of participants in each group, and that's okay. So first thing, find the mean and degrees of freedom for sample 1 and the mean and degrees of freedom for sample 2. So pause it here, go ahead and do that. Got a lot. And once you've gotten that, then do your deviation and your deviation square. So whatever your mean is here for group 1, take the score minus the mean, that'll be your deviation score, then square it. In this case, score minus the mean, that's your deviation score, and then square it. And then do the same for these 5. So whatever the mean is for virtual reality, score minus the mean is your deviation score, and then square it. Go ahead and do all of those. And when you do, we have, in this case, 6 people. The mean was 3, degrees of freedom is 5, and your sums of squares was 4, adding those up. Remember, every time you do your square, you square your deviation scores, these will all be positive. And then for virtual reality, we had 5 people in total, so degrees of freedom was 4. The mean was 4.8, and then sums of squares was 6.8. So hopefully you got those. Now let's identify the population and choose our statistical test. So the populations that we're looking at are all students who take an in-person driving lesson, and we're comparing that to all students who take a virtual reality driving lesson. Of course, we can't test the population, that's too many people, so we just take a sample. The independent variable is type of driving lesson, and the levels that we're looking at are in-person and virtual reality. The dependent variable, what we're measuring, are errors on the driving test, and we're doing an independent samples t-test because we're looking at 2 separate groups of people. State our hypotheses. Try to write these out for a second. And if you've already done that, so pause it. Hopefully you see this. The null hypothesis is that the mean for group 1 should be equal to the mean number of errors for group 2. So this is really, the mean number of errors on the driving test for students who take the in-person class should be equal to the mean number of errors for students who take the virtual reality class. And the alternative hypothesis is that the mean number of errors for students who take the in-person class will not be equal to the mean number of errors for students who take the virtual reality driving test. When you're using these subscripts of 1 and 2, remember to take a note of what 1 is equal to, like 1 in this case is in-person and 2 is virtual reality. Be sure you note that and follow that same those same symbols throughout the whole problem. All right, now we've got to do pooled variance and standard error. So you've got your sums of squares, you've got your degrees of freedom, you'll be able to find pooled variance, and then once you have the pooled variance, you plug it in here. Pooled variance over the number of people in group 1 plus pooled variance, number of people in group 2. So pause this here and see if you can get this. And hopefully you're getting 4, in this case sums of squares for group 1 was 4, plus sums of squares for group 2 was 6.8, over degrees of freedom for group 1 is 5, plus degrees of freedom for group 2 is 4, which gives you 10.8 over 9, or 1.2. Once you have that, we take our 1.2 and we plug it in to this equation. So we have 1.2 over 6 plus 1.2 over 5. We're going to take the square root of that. Remember, you do this division, and you do this division, so this is the square root of 0.20 plus 0.24, which then when you add them together is the square root of 0.44, which gives you estimated standard error of 0.66. Okay. Now we've got to determine our critical value, and did I give you an alpha level? I'm going to say 0.05. Let's check. Yep, 0.05. Remember, you need to fill in degrees of freedom for the whole test. So it's either degrees of freedom for group 1 plus degrees of freedom for group 2, or total number of participants minus 2. So try to look that up on your own t-table and see if you can find the critical value. Pause it here. And if you have done that, we've got degrees of freedom as 9, because we can do 5 plus 4 is 9, or total number of participants was 11 minus 2, which is 9. And our critical value at an alpha level of 0.05 is plus or minus 2.262. Again, you could draw this out. Yes. So we're doing plus or minus 2.262 minus 2.262. Those are our critical values. And this is it, how we found it, right? We had degrees of freedom 9, go over here, 2.262, that's it, our 0.05 alpha level in two tails. All right, time to calculate your test statistic, which is group 1, mean of group 1, minus mean of group 2, minus, remember this is always 0, over your estimated standard error. So try to work that out. Pause this here for a minute. And if you do, we had 3 errors minus 4.8 minus 0 over 0.66, which gives us negative 2.72. So over here, negative 2.72 is over here. And what are we going to do? Well, I'm going to let you figure it out. Take a second to write out your statistical conclusion, your substantiative conclusion. Use the format that I've been showing you in the previous example and see if you can write this out. So again, pause it here. And then you would have rejected the null. Our obtained t of negative 2.72 is more extreme than the critical t of plus or minus 2.262. Substantiative conclusion is we're going to reject the null. There's a statistically significant difference between number of errors made on a driving test by students who took an in-person driving course and those who took a virtual reality driving course. And which direction? Now look, we've got a negative sign here. And if you recall, our t is all the way here in this negative direction. So what is that saying to us? It's saying that students that took the in-person driving course made significantly less errors or fewer errors than those who took a virtual reality driving course. So actually, in this case, a negative z-score is a good thing, or negative t-score is a good thing. You want to have less errors. So it really matters what the problem is that you're working on. If you're talking about errors, you would like a negative score because you want to be below average on errors. If we're talking about, score on your statistics final, you want a positive t-score. You want to be above the mean. So you do have to look at the problem to figure out, is a negative score good or bad? What if the mean for group 1 is 3 and the mean for group 2 in terms of errors was 3.9? If nothing else changed, our t would then be negative 1.56. So coming back over here, our t would now be here, negative 1.56. So now what would your conclusions look like? Give you 1 second for you to, or take as long as you want actually, to write out your conclusions now. Pause it here so we can give you a chance. And your conclusions would now be that you would fail to reject the null or obtain t of negative 1.56 is less extreme than the critical t of plus or minus 2.262. Based on our data, we fail to reject the null. There's no statistically significant difference between number of errors made on a driving test by students who took an in-person driving course and those who took the virtual reality driving course. All right, hopefully you're able to follow along to this point. There are 2 last pieces that we always have to do. We're going to measure Cohen's d, or your effect size. And effect size is here at sample mean 1 minus sample mean 2 divided by the square root of variance. And remember, what's the square root of variance? Standard deviation. This is very much the formula we've always used. Where when you're looking at Cohen's d, you're looking at the mean difference divided by standard deviation, which is the metric that we use. In this case, we didn't compute standard deviation, but we know standard deviation is the square root of variance, and we do have that. So in this case, we've got 79, the mean of group. Oh, this is going back to the example with the physical health score. For children whose parents are married, which is 79, minus the physical health score of children whose parents are getting divorced, which is 68, over the square root of variance, which is the square root of 102.89. When you do that, you get a 1.08, which is a large effect. Remember, I gave you that breakdown a small effect being around 0.2, medium effect around 0.5, and a large effect about 0.8. So this is 1.08, it's large. And what that means, again, this is in standard deviation units. On average, we can expect children whose parents are married to have a physical health score that is 1.08 standard deviations higher than children whose parents are going through divorce. So when we just do our significance test and we end up with a, when we reject the null, all we're saying is there is an effect of parents' marital status on children's physical health scores. But when we add Cohen's d, we are now giving ourselves some information about the size of the effect. And in this case, you're expecting a standard deviation, a little bit more than a standard deviation change in physical health score between these groups. So that gives you a little more information. Last is confidence intervals. Confidence intervals for a two-sample test tells us it's really a confidence interval around the difference between your sample means. So in the parents married versus going through divorce example, here's our formula, is mean of group 1 minus mean of group 2, plus or minus the t, and this is the t you look up in the table. This is not the t you compute. This is your critical t from the t table, times standard error. So in this case is 79 minus 68, or an 11-point difference, plus or minus 2.101 times 5, so that's the t we looked up in the table, times standard error that we computed, 4.54, which gives us 11 plus or minus 9.54. So when you do 11 minus 9.54, you get 1.46. And 11 plus 9.54 gets you 20.54. This is our confidence interval. And what we're saying is that this is the confidence interval of the difference, this 11-point difference, between our two sample means. So what we said is, we tested a sample. Remember, there were 20 people. There were 10 children in the parents married group and 10 people in the children whose parents are going through divorce. And their sample mean difference was 11, right? There was 79 was the physical health score in the parents married, and 68 is the physical health score of children whose parents are going through divorce. There was an 11-point difference in our sample. But remember, we don't really care about our sample. We care about what's happening in the population, where there are millions and millions of children whose parents are married and millions of children whose parents are going through divorce. So when we create this confidence interval, we take our sample mean as our best starting point. We use variability, we use number of subjects, we use all sorts of things to kind of go into this computation. And what this tells us is that in the population, we are 95% confident, and remember, we're 95% confident because we looked up a t at the 0.05 level. So that tells us that's a 5% chance we're making a type 1 error, which also means we're 95% confident we're not. So in the population, we're 95% confident that the difference in physical health scores between children whose parents are married versus children whose parents are going through divorce will be somewhere between 1.46 and 20.54 points. This is what we expect to see in terms of the difference in physical health score between the groups in the population. Okay? If your confidence interval includes 0, what does that mean? That would mean, like, if this confidence interval started at a negative number and ended, let's say, at 20.54, so 0 is included in the confidence interval. Well, what does that tell us? That tells us that we don't know very much. We're either saying, if it's a negative number here, one group is higher than the other, or 0 is in the confidence interval, so that means that there may be no difference between the groups, or the other group is higher than the first group. basically it's saying we don't know anything. And if the confidence interval includes 0, then the difference between the groups will not be statistically significant. These two things will always go together. That if your confidence interval includes 0, you will have already failed to reject the null. And if you do reject the null, like we did in this case, your confidence interval will not include 0. Okay. You could think about when you would use a z-test over a t-test. What kind of study would you use for an independent samples t-test? And what kind of study would you use for a paired samples t-test to start thinking of how you would use these tests for different studies? And that's going to be important as we move on to our next exam coming up, which I'll give you more information soon. All right, I hope that helped you understand this chapter. Thank you very much. As always, email me with any questions you have. Thanks.